Hello everyone, and thanks for watching Edupedia World Videos. In the previous videos we learned about the gravitational force and gravitational field, and in this video we'll move on to potential energy. First, let's take a brief recap of what we learned so far. If we have an object of mass m1 and another object of mass m2, then they will attract each other with equal and opposite forces, which will have magnitude F, and the directions will be opposite by Newton's third law. The magnitude of F is equal to g m1 m2 by r square, where r is the distance between the two particles. Now, if we take one of these particles to be at the origin, it makes it easier for us to calculate various quantities. So let's say this is the origin, this is the x, y and z axis. This vector is now r, which is the position vector of m2 if we take m1 to be the origin. Right. Now if we wanted to write the force on m2 due to m1, that would have this magnitude and the direction would be towards m1. Now r is the position vector of m2, so the direction or unit vector in this direction would be r hat. So the unit vector in the opposite direction would be minus r hat. So the force experienced by m2 due to m1 would actually be minus g m1 m2 by r squared r hat. This is the magnitude and minus r hat is the direction. Right. Now, if we wanted to calculate this particular quantity for a number of different masses m2, then we would find out that the magnitude of the force is proportional to m2. Right, that we can directly see that from this formula. So if m2 is 5 kg, then the mass would be 5 times what it would, the force would be 5 times what it would be if m2 was 1 kg. Right, so m2 just plays a small role as sort of a constant of proportionality. So this particular quantity, which we get if we put m2 equal to 1, we label this as the gravitational field. In this case, it is simply the force experienced by m2 per unit mass. Right. So whatever mass is there, we can simply multiply that by the force experienced by a mass of 1 kg, and that will give me the force experienced by that particular mass. So in this case, we can see from this formula, it will be minus g m1 by r squared r hat. What is the purpose of this gravitational field? Now we can simply get the force on any different particle by multiplying this gravitational field by the mass of that particle. Now we know that gravitational force is a conservative force, that is, the work done by the force does not depend on the initial and final points, so we should be able to define the potential energy corresponding to the gravitational force. So let's look at that now. Our situation is, we have an origin where we have an object of mass m1 and we have another object of mass m2. Right, the position vector of m2 is r at any point. Right. So we want to find out, let's say, because in talking about gravitational potential energy, it only depends on the configuration. Right, that is, for two particles, that would mean the distance between the two particles. So let's say m2 was initially at some position vector r1, and finally it is taken either to the left or right, and its final position vector is r2. So we are taking m2 from r1 to r2, right, and we want to find out the difference in potential energy at r1 and r2, right, because remember we talked about potential energy earlier and we saw that potential energy does not ever have a particular value of 0. Right, we are free to choose 0 anywhere, and the only thing that is constant is the potential energy difference between two configurations. So if m2 is at r1, then there will be some potential energy, and if m2 is at r2, there will be some different potential energy. Those two values depend on what value we choose to be the potential energy 0. But the difference between those two values will not depend on our reference point. So that is the important thing. So I'll label it as u r2 minus u r1. And what is it? Let's look at the definition of potential energy we saw earlier. Potential energy was the negative of the work done by the conservative internal forces. right? So potential energy only makes sense if we are talking about internal forces. Potential energy is defined only for conservative internal forces. So in this case, we'll take M1 and M2 combined to be a system, and we are moving M2 and M1 is held stationary. So there will be a force of attraction between these two. This particular force on M1 will do no work because we are keeping M1 stationary. There will be another force which we are applying on M1 to keep it stationary, but that force will also not do any work, right? The only work done will be due to the gravitational force and the gravitational force on M2. So let's look at that. It will be the negative of the integral of, now the work done by the gravitational force will be F dot dr. What is F? The gravitational force on M2. It is minus g m1 m2 by r squared r hat, right? So that is towards the left. So if we talk about F dot dr, then r hat and dr have the same direction, which is towards the right. So it will come out to be minus g m1 m2 by r square dr. Right, now the vectors have gone away because we take the dot product, and r hat dot dr hat will simply be the magnitude of dr because mod of r is 1 and they both face in the same direction. What will be the limits? We are taking r from r1 to r2. Now r1 is the magnitude of the position vector r1 and r2 is the magnitude of the position vector r2. So I'll repeat this once again. Minus gm1 m2 by r squared dr is the work done by the gravitational force. Why is it negative? Because the gravitational force is towards the left. However, we are taking the particle towards the right. Right, dr is always in the positive direction of r. This is a very big point which you might have confusion sometimes. So why did we not take minus dr in this case? That is decided by the limits. The limits are going from r1 to r2. r1 is this point and r2 is this point. So obviously we are going towards the left, but dr is a small change in r. So if we change r by a small amount, then it would go towards the right because dr is always assumed to be a small positive quantity. So in this case, this minus and this minus will cancel and we'll get r1 to r2 g m1 m2 by r squared dr, which will give me, this will be r to the power minus 2, so we'll get r to the power minus 1 by minus 1, and that minus 1 means we'll have to take this limit first. So this gives us g m1 m2 1 by r1 minus 1 by r2. This is u of r2 minus u of r1. Right. This is the most important formula in gravitational potential energy, and every other formula we see from now will ultimately be derived from this formula. So anytime we take an object from a position, now in this case you see that r1 and r2 are just the magnitudes, the direction does not matter. So we could take m1 to be fixed at this point and m2 to go from this point to this point, or anywhere on this circle from this point to this point. It doesn't matter because the only thing that matters is the distance between the 2 points, not the direction. Right. So if we take an object from r1 to r2, the net gravitational work done, the work done by the gravitational force, will be gm1 m2 1 by r2 minus 1 by r1, and the potential energy change will be the negative of the work done. Right, so let's look at this formula in a little bit more detail. U of r2 minus u of r1 is equal to gm1 m2 1 by r1 minus 1 by r2. Right, now this formula can be seen as, if we write u of r is equal to minus gm1 m2 by r, then we see we've done a little mathematical trick, and we see that if I put r is equal to r2 and then r is equal to r1, this would give me this result. Right. So, and another thing we could do is, we haven't yet chosen a reference point. Right now we are only talking about the difference between potential energy if m2 was at r1 on r2. Right. So let's take a reference point r0. In that case, u of r2 minus u of r0 will simply be u of r2, because the potential energy at the reference point is 0. That is the definition of the reference point, and that will be equal to gm1 m2 1 by r0 minus 1 by r2. Now, due to the nature of this formula, one thing we generally do in the case of gravitation and also actually in the case of electric forces is we take a reference point to be at r is equal to infinity. That means our reference point, our point of zero potential energy, is taken when the two particles are extremely far away, so far away in fact that they do not exert any substantial force on each other. So if we take r naught is equal to infinity, then this term 1 by infinity will become 0. And we get u of r2 is equal to minus gm1 m2 by r2, which is another way of getting this formula. So this particular formula, the potential energy of any object when it is at a distance r2 is minus gm1 m2 by r2. This is not always valid. This is an important point. This is valid only if the potential at r is equal to infinity is taken to be 0. That does not need to happen. For example, let's say if the potential at infinity is taken to be 0 and the potential at a particular point is minus 5. In that case, if I take the potential at infinity to be 10, then the potential at every other point in space will simply be increased by 10. It will not change the difference between the potential and energy at any two configurations, which is the only thing that ever matters. Right? So the actual potential energy is irrelevant and the difference between potential energy is the only thing that's relevant. That is true for potential energy in any case. In the case of gravitational potential energy, because of the nature of this formula 1 by r, we generally choose r is equal to infinity to be our reference point. In that case, the potential energy is defined as minus gm1 m2 by r. Now, just like we have a relationship between gravitational force and gravitational field, similarly we have a relationship between potential energy and a quantity called potential. So what is the relationship between force and field? We know that the force is proportional to the mass of the object which we are studying, right? So what we do is we generally take the mass of the object to be a unit mass, that is generally 1 kg, and the force is called the field, and the force on any other mass will simply be the mass multiplied by the field. This is the same thing we'll do in potential energy. So the potential energy was defined for a standard mass m2, and we found that to be minus gm1 m2 by r. So we know that if we keep changing m2, the potential energy will be a particular quantity multiplied by m2. So we call this particular quantity a potential. And the use for this is, it should be clear to you by now because you know the use of talking in terms of field as opposed to force, is that now we can simply talk about potential just like field as a property of space. We do not need to worry about what is the configuration that caused this particular potential. If we are given the potential and we are given the mass of the particle which we are studying, we can calculate everything there is to know. We are not interested in this particular inner formula, how this potential came to be. We are just interested in what this total quantity may be. So in that case, the potential energy between 2 points, let's say R2 and minus, let's say at R1, is simply the potential at R2 minus potential at R1 minus M2. Keep in mind M2 and M1 are not right now symmetrical. We are studying M2 and M1 is our source of potential. Right. Now if we take R1 to be the reference point, then we simply get V of R2 is equal to U of R2 by M2, because at the reference point both the potential and the potential energy will be 0. And if we take the reference point to be R is equal to infinity, then we get V of R is equal to minus G M1 by R. Again, this upper formula is always true, the lower formula only true when we take the potential at infinity to be 0. So let's look at the potentials due to some important standard quantities. We saw the the gravitational force and the gravitational field due to certain standard geometric quantities, and the calculation of the potential is pretty much similar. So the first thing we saw was a single point charge. In that case, we saw that the gravitational field was minus g, if this has a mass m, was minus gm by r square r hat. That means any particle of any random mass m1 would experience a force of m1e. As we change m1, m1e might change, but this quantity e still remains the same. It is only a property of the source. Similarly, the potential would be minus gm by r. Now, the important thing to note, potential energy and potential are both scalars, whereas gravitational field and gravitational force are vectors. And that is why you'll often see that we try to solve problems in terms of potential and potential energy as opposed to fields or forces, because in that case it becomes a scalar problem, and scalar problems are generally much easier to solve than vector problems. Right. So this was the standard case. Let's look at the case which is slightly more complicated than this. We had a ring and we had a distance r from this, and the radius of the ring was a, and the mass of the total ring was capital M, and we wanted to find out the gravitational field at this point. We calculated the gravitational field and we found out it was minus gm r by a squared plus r squared to the power 3 by 2. Right. Obviously r hat, that is towards the center. And the way we found out was, I'm not going to go into the complete details, but we took small random elements. We took an element here and we took an element here, and we took different elements, and we calculated the gravitational field due to each element. We found out that their vertical components would all end up cancelling out, because two diametrically opposite points would have the opposite vertical components but horizontal components in the same direction. And we ultimately took the horizontal component of one element and we integrated it to get the total horizontal component of the gravitational field. The same thing needs to be done for potential, except we don't need to take components because these are scalars. So if we take a small element dm, then the distance of that element from this point is root of r squared plus a squared. So the small potential due to that element would be minus g dm by root of r squared plus a squared. So if you calculate it due to all of them, you simply integrate it. R, A and G are all constants, so you get minus gm by root of r squared plus a squared. This is the potential at R. Right. So this is one way to calculate the potential for different quantities. You can just take the potential of an infinitesimal element and you can try to integrate it to get the total potential. However, there's another way you can calculate potential for this quantity, and that is by looking at the electric field. So let's look at the relationship between potential and electric field for a second. We know that the change in potential energy, U of R2 minus U of R1, is the negative of the work done by internal forces. This is sort of the definition of potential energy. So in this case, we can say U of R2 minus U of R1 is equal to minus integral of R1 to R2 F dot dr, where F is the gravitational force. Right. Now we have relationships which is V of R2 minus V of R1 is equal to U of R2 minus U of R1 by M. This M is the mass of the particle which is being analyzed, and similarly we know that the electric field is equal to the force divided by the mass. Right. So we divide both these quantities by the mass. What we get is V of R2 minus V of R1 is equal to minus integral of E dot dr R1 to R2. Right. This is just this whole result divided by the mass. Now, if we take R1 to be infinity, which is generally what we take to be the reference point, then V of R1 will become 0. So we'll get V of R2. Now I'm just going to write R2 as R. That will be minus integral of R1 is now infinity to R E dot dr. Now this is a very important result. This gives you the relationship between electric field and electric potential, right? So if you want to calculate the potential due to a certain random configuration of masses at a particular point, you can either calculate the potential due to each individually and add them up, or if somehow for some reason you know the electric field due to these, then you can simply move a particle from infinity to this point and calculate the integral of E dot dr from infinity to r and take the negative sign. And that is another way of calculating the potential. So we can look at this and we can get the potential by this way as well. So we go back to our original case, the radius is a, this distance is r. We know the electric field is minus gmr by a square plus r square to the power 3 by 2. If you want to know how to get this, you should look at the video for electric field. We did this in detail in that case. So the potential at r would be minus integral of this dot dr. So this minus and this minus will cancel, so I'll just remove it. Infinity to r gmr by a square plus r square to the power 3 by 2 dr. You know how to solve these. For simplicity, I'll just multiply it by 2 and I'll divide by 2. So the derivative of a squared plus r squared will be 2r. So I can take a squared plus r squared to be t, then dt by dr will simply be 2r. So 2r dr will be dt. So this will be integral of infinity to is a squared plus r squared. You'll have gm by 2 t to the power 3 by 2 dt. So that will give me gm by 2. T to the power minus 3 by 2 has an integral of t to the power minus 1 by 2 by minus 1 by 2, that is multiplied by minus 2, and the limits will be from infinity to a squared plus r squared. This will give me 0. These two will cancel, so that will give me minus gm by root of a squared plus r squared, which is the same result we got previously by just calculating it individually. For each element, it would be minus g dm by root of a squared plus r squared. A and r are constant, g is a constant, integrated, minus gm by a squared plus r squared. So in this case, the first method would have been easier, but I showed you the second method because you need to know both methods, right? For the future, you can calculate the potential either directly or if you know the electric field. Now let's look at this relation a little bit further for a second. V of r is equal to minus integral of infinity to r e dot dr. Now, because v and e both can be added, so v1 plus v2 plus v3 will be minus integral of infinity to r e1 plus e2 plus e3 dot dr. So this is not just valid due to one point charge, this is valid due to a collection of charges as well. If you have 15 different charges placed in different positions, they need not even be point charges, and you need to find the potential at a particular point due to these, then you can either find the potential due to each one and add them up, or if you know the electric field. This only works if you knew the electric field for some reason. Then you can just use this particular integral, and why this particular configuration produces that charge will not really be important. Now you can invert this formula. If v is the integral of e, then e is the derivative of v. So by inverting this formula, we can get electric field if we are given the potential, and the potential is generally a scalar function. So if we invert this, we can get, so we could differentiate this upper relation with respect to r, and that will basically give us d of v is minus e dot dr. Now dr is dx I cap plus dy j cap plus dz k cap, right? So e dot dr will be ex dx plus ey dy plus ez dz. Now if dy and dz are 0, then this relation implies ex is equal to minus dv by dx. This relation is only true when dy and dz are 0. Now you've seen this thing before in mathematics. This could actually be written as, this is if dy equal to dz equal to 0, and this is actually written as the partial derivative of v with respect to x. The partial, for example, let's say v is given to us as 3xy plus xy square plus z cube. Then Ex will be the electric field component in the x direction, and that will be minus del v by del x. That means differentiating v with respect to x, keeping y and z constant. So in this case, that will be minus 3y minus y, right? So that will be minus 4y. This is actually this is actually 4xy. I tried to make this in a hurry, so I made up something silly, right? So anyway, you get the point. Ex is minus del v by del x. Ey is minus del v by del y, and Ez is minus del v by del z. So not only do we know how to calculate the potential from the electric field, now we know if we were given the electric field, if we were given the potential, then we could calculate the electric field as well. This formula is just the opposite of this formula. A final thing, let's look at the two other geometrical quantities which were important after the ring: a spherical shell and a solid sphere. For a spherical shell of radius r, what we calculated was, if we wanted to find out at a distance a from the center, then the electric field was minus gm, if the total mass is m, the gravitational field was minus gm by a squared r hat, that is towards the center, if a was outside the sphere, that is if a was greater than r, and it was 0 if a was less than r, right? That is inside this hollow sphere there was no electric field. From this we can get the potential. The potential is simply minus gm by a for a greater than r. You can get that simply by integrating this. This is just the standard formula for electric field. And inside the hollow sphere there is no electric field, right? If there is no electric field, that means Ex is del v by del x. That means del v by del x is 0, del v by del y is 0, del v by del z is 0. A lot of students make this mistake. They assume that this means the potential is 0. This does not mean that the potential is 0. This means that the potential is constant, right? Now if the potential is a constant, that means the potential will be the same at the center as it is at the surface. At the surface, these 2 points coincide when a is equal to r. So at the surface it is minus gm by r. So it is minus gm by r everywhere where a is less than r, right? The potential you cannot choose to be 0. You have already chosen a potential to be 0 at infinity. If the potential at infinity is 0, then it would take us some work to get the particle from infinity to this point, right? As it happens, that work would be the same if we had to get it to this point or this point or this point, because inside the electric field is 0. So the potential inside a spherical shell is constant. The last case, let's look at a solid sphere. For a solid sphere of radius r, the electric field, this was the most important formula, that for both solid and hollow spheres, outside they behave exactly as a point charge of the same mass placed at its center, right? So this was minus gm by a square r hat if a was greater than r. However, if a was less than r, this became minus gm r by a cube r hat. Again it was towards the center. So from this we can get the potential directly. Now if the electric field is the same as that of a point mass at the center, then the potential has to be same as that of a point mass at the center. So it was minus gm by a for a greater than r. For a less than r, I'm not going to do it, but you can do it easily enough. All you need to do is integrate this, and it will come out to be minus minus gm by 2r cube 3r squared minus a squared. I think I made a mistake. This should be a and this should be r actually. R cube, yeah. This is for a less than r. The last formula you can derive, you can actually try to do it by the longer method if you want. Calculate the potential due to each spherical shell and integrate it, or you can use these two integrals. Remember, if you are integrating from r is equal to infinity to this point, you have to break it into two integrals, from infinity to this point because the electric field is different there, and from this point to this point where this formula is to be used. This completes electric potential energy and gravitational potential. In the next video, we'll see and we'll discuss the motion of planets and satellites. Thank you.